We want to get into questions about computer forms of solving various circuit questions. And in particular, talking about node and mesh solutions. Well, mesh will be in a different lecture. Node solutions typically are one of the more useful ones when you're doing this by hand, but both of them have their opportunities and properties. Now, typically you don't need to do a lot of these. It's really very important to know how this works. It's also very important to know, I would say, to know what the computers are doing and how you're setting up some of these kinds of problems. It's sometimes also useful because you're going to be, using this either for a physical analogy or you're using this as a way to talk about, say, potential parts of computing and solving linear systems. In any sort, it's at least good to have these kind of backgrounds, even though in a lot of times classic solutions of linear systems, you're not going to use this stuff. So what we're going to look at here is it's a systematic approach, starting with KCL at multiple nodes. And in this case, we have two nodes. We're going to use the same circuit for a number of different linear circuit problems, which just has two voltage sources and a bunch of resistors. It has two nodes, and if you look at it, it's two nodes, E1 and E2. And we kind of use those just classically for node voltages. They're meant to be voltages here. And those are the things I'd like to solve for. And typically what it means is I'm going to write KCL around this node, which I'm going to call node 1. And I'll write KCL around node 2, and I'll get that. And typically, if I work through the math, I'm going to get an equation that has E1, and I'll have a whole bunch, I have sort of the sum of all of the conductances. And for the second one, I'm going to have E2 with the sum of its conductances. I'm going to have a term that's going to be related to the voltages. And I'm also going to have some cross terms as well. In this term, the one cross term between E1 and E2 is R5. And so what I can do, and I'm showing this in a very simple case, because it'll be a simple matrix, is that I can almost always write down a linear system. You could start from here and find that I'm going to get an equation which is going to be a conductance matrix times voltage vector. Conductance matrix being a capital G, voltage matrix being lowercase v but still bold, and I being a current. It's sort of a way of looking at Ohm's law, but in a matrix format. And I could do that and then write down what my value is for G. And one of the things I notice, and this is one of the things where it becomes helpful, is that I can just write down G, at least the diagonal terms, is going to be the sum of all the conductances at any one node. This is actually quite useful and just kind of sometimes a useful check when you're actually doing other hand analysis of circuits to kind of think, what should I be seeing when I put this together? Okay, so this is one of the things we would do. On the cross terms, they're negative, and they tend to be whatever conductances are between those nodes. If I had 3 nodes or 4 nodes, then we would look at those cross nodes. And so sometimes you can just start to put this together for a larger circuit, and it works. It tends to be very valuable if the circuit is not 2 nodes or 3 nodes, but it happens to be like, 50 or 60 nodes, and I want to have a program run this. I may want to have some way that I can write this down and generate this accordingly. I may also want to write computer code that actually extracts out these values from something else and then, automatically generates it. So this is where it's kind of useful to know, and it's good intuition. There's one voltage vector V, and then the I is what's left over, effectively thinking about other currents that are getting brought in effectively because of the other voltage sources. If I had current sources, that would change. If I had voltage control current sources and other voltage control sources, I'd also see this. So all of this turns out to be, it gives you a whole range of possibilities. And so this is where it's just good to kind of get a sense of what the intuition is. And there's a whole range of things to know, but it's just good to be aware of it. A couple other things in terms of the math, in case you haven't thought about this. This particular matrix for G is always going to be positive definite. I guess in theory it's probably positive semi-definite, but basically it's always positive definite. And that's really quite useful if you're going to be, say, using it as a way to use a relaxation, so it becomes a differential equation, and I solve that. And so it allows me to kind of do some very straightforward things. If I write down a matrix like this, if I then work in MATLAB, It's very easy to invert a matrix or solve these kinds of problems. And that's kind of why we like these things, is that there's very straightforward ways to talk about these solutions. So in general, there's a tremendous amount one can do with these, but it's just important to know what it is. But in typical day-to-day analysis, we don't typically use this very often, but it is helpful, and it's really important to at least be aware of it and allow it to be one possibility you can use.